Hello, I'm going to talk about Thomas Harriot and the work he did on the coins of England at the beginning of the 17th century. None of Harriot's mathematical work was published in his lifetime, but some 8,000 pages of it are now available online. Among these pages, there are a few that deal with the matters of coinage. And, for example, we shall be talking about a very early application of symbolic algebra to a practical problem, about one of the first examples of the use of hydrostatic weighing to measure the density of objects, and finally an awful lot of complex arithmetical calculations that may have influenced the affairs of the nation. It's worth noting, I think, that Isaac Newton, 100 years later, was employed to do this kind of calculation, and indeed what he did had a profound influence on the course of economic history in the 19th and 20th centuries. So, it's necessary to begin with a crash course, a very short introduction to the matters of coinage and the use of precious metals for that purpose. In the Roman times, Romano-British times, 2,000 years ago, here is a silver coin of Augustus, very impressive coin made of good silver, and these are often found in this country. However, many of the denarii that are found in this country are not made of pure silver like the Augustus coin that we saw. Over the next 200 years or so after Augustus, the denarius was gradually debased, and eventually it became a coin essentially made of copper, occasionally with a rather pathetic attempt to make it look like silver by having a sort of silver coating. The Romans were able to make these debased denarii serve the purposes for which they wished them to be used in trade and so on, because of their absolute power at that time. But over the next 1,000 years, matters became very much more complicated. Many countries, nations, began minting their own silver coins, and these were of varying degrees of purity. Fortunately, however, by the 1200s, there were mathematical methods available which enabled these problems to be coped with. And so we find the classic book of Leonardo of Pisa, Fibonacci, the Liber Abaci, first written in 1202, contains a tremendous amount of material on the fineness, purity that is, of silver coins and the calculations that are required when these problems have to be dealt with. Here is one example from the English translation by Sigler. I'm not going to go through this particular one because I'm actually going to give you a much simpler version in a few minutes. But it's obviously important to notice that Fibonacci was using, first of all, the Hindu Arabic numerals, and secondly, of course, the method of calculating with them by what we might call pen reckoning. In other words, writing down the figures and rubbing them out and moving them around, rather than just the counters on a board, which had been the classic method of dealing with arithmetical calculations. So coming back to England, by the end of the 13th century, the English had already decided that their coinage was going to be good silver. In fact, it was going to be the sterling standard, which was very close to, if not exactly the same as, what we now call sterling silver, which is 92.5% pure silver. Other countries were producing so-called silver coins of different finenesses, and most worrying from the English point of view was that some of these were just plain imitations of the sterling penny, but with much less silver. So here is a continental imitation of a sterling made around the same time, and it has only 25% silver in it. Of course, this created tremendous problems, in particular for the people who had to make the coins and ensure that they were of the correct standard. So by 1285, we have a Latin treatise on the new money written by a mint man in England who was trying to explain to Boris the difficulties of making the coins of the correct standard. And he gives an artificial example with simple numbers. Here it is. Suppose I have to alloy the money to be 9 pence fine, and I have bullion, that is, money has been brought to my mint, which is 11 pence fine, and some which is 4 pence fine. How am I going to mix these different types of bullion in order to make the correct standard? So bullion 11 pence fine means 11 parts of it in 12 are pure silver. A penny was 1/12 of a shilling, so 11 pence means 11 parts in 12. And the worse bullion, which was only 4 pence fine, has only 4 parts silver in 12. And out of these two things, one better, one worse, the mint man has to make silver, which is 9 pence fine, 9 parts silver in 12. Problem is how to combine this better metal and this worse metal in order to produce the required standard. Well, the intuition is actually quite simple. 11/12 is better by 2 than the required standard, which is 9, and 4/12 is worse by 5. So it's pretty clear that the metals should be combined in the inverse ratio, that is 5 of the better and 2 of the worse. This is the conclusion reached in the treatise. It's explained in words, but we can see it in modern notation, which must remember it was not available to the workers, the arithmeticians in the 13th century, because 5 times 11 plus 2 times 4, that's 5 lots of 11 fine and 2 lots of 4 fine. That adds up to 63, and 5 plus 2 is 7, so we've got 7 lots altogether, and 63 is 7 times 9, so the bullion that the money that we are creating, the silver that we are creating, is in fact 9 pence fine. This technique became known as alligation, and it was one of the standard topics in texts on arithmetic, the manuscripts written in the time of Fibonacci and thereafter, and from the end of the 15th century onwards in the printed books, which began to be produced in large numbers. And so we shall go on in the next part to see how this topic of alligation was the thing that first attracted me to Harriot's work. So we can now move on to the work of Thomas Harriot, which was done around 1600. Here is the item from Harriot's papers which first drew my attention to his work on this topic. It is in fact a proof, a general proof, of the rule of alligation that we've just been discussing. Now, the important point here is that this method and this notation was in fact quite new at this time. All the algebraic work, for example, on cubic equations that had been done in the 16th century was done with a cumbersome notation involving words and symbols. And Harriot was among the first to use what we would now regard as modern algebraic notation. So what he is doing here is, you can see towards the left-hand side, the letters B, C, and D. B is the fineness of some better metal, C is the fineness required for the standard metal, and D is the fineness of some worse metal. And to the left of that, Harriot has written the rule, that is, take D minus C parts of the better and C minus B parts of the worse to get D minus B parts altogether. And then the rest on the right is simply an algebraic calculation in exactly the terms we would use today, showing that if we do that, then in fact the mixture is in fact of the correct fineness C as required. So just a quick rundown on Harriot. He was born in Oxfordshire in 1560. We don't know any details of that. We do know he went to Oxford University. We do know that between about 1590 and 1620, he produced a vast amount of mathematical work, over 800 pages of it, all of which was unpublished in his lifetime. The highlight of this was probably his use of a telescope to examine the surface of the moon in 1609, and it's noteworthy that he did this before the much more well-known experiments of Galileo, and he died in London in 1621. So how was he able to do all this work? Well, he had the support of two famous patrons. Walter Raleigh had recruited Harriot for one of his voyages to the New World because he required expert assistance with the navigation. And in fact, Harriot was able to make some significant advances in the techniques of calculation required in navigational matters. Harriot remained in touch with Raleigh, but he was lucky enough to be taken on by Henry Percy, 9th Earl of Northumberland, who had a large estate in West London, Sion House, and he installed Harriot there in a comfortable house where he was able to carry out his mathematical and scientific work without any external pressures. Percy is also important to our story because soon after James I ascended the throne of England in 1603, Henry Percy was appointed to the Privy Council. And one of the important tasks of the Henry Privy Council and King James was to unify the coinages of Scotland and England. Both countries had been producing gold and silver coins, but they were confusingly, apparently similar in name, but different in fact. And so the Privy Council set out to do something which, in modern terms, is probably comparable with the decimalization of the English coinage, which of course didn't take place until 1971. Here is a proclamation that was produced towards the end of 1604 and sets out what they proposed to do regarding the gold and silver coins. So there were to be gold coins, and you can see on the right-hand side that £37 4 shillings worth of these gold coins was to be made out of 1 pound troy of metal. This metal was to be crown gold, as it was called, which was what we would now call 22 carats fine. That is, 22 parts out of 24 were pure gold. The numbers in the tables are the weights of the individual coins based upon the tariff that's set out on the right-hand side. So the top line tells you what a 1 pound coin ought to weigh in the light of that statement. The bottom half is about the silver coins, and it tells you that these, which were now by now made of what we call sterling silver, definitely 92.5% pure silver. Of these, 3 pounds 2 shillings worth were to be made from the same weight of metal, that is 1 pound troy. Now, an implicit fact, which those of us who remember how to do arithmetic with pounds, shillings, and pence will almost certainly have spotted, was the ratio between the values of the gold and silver coins. In other words, the amount of gold that was worth 37 pounds 4 shillings was the same as the weight of silver that was worth 3 pounds 2 shillings. And the ratio between these numbers is in fact 12 to 1. It turns out that this is not the whole story about the ratio. The ratio was particularly important because in the international markets, if the ratio in another country was different from the one adopted here, then money could be made by merchants simply by arbitrage, that is, by taking gold abroad and exchanging it for silver and then reversing, bringing the silver back and changing it into gold again, or vice versa. So Harriot set out to do some calculations about the ratio. And in fact, he wasn't interested at first in the new coins. He was interested in some old gold coins. These were the coins known as angels. Here is one from the time probably of Henry VIII. Many of these were still around. They had been produced throughout the reigns of Henry VIII and Elizabeth, and indeed before that. And Harriot wished to establish the value of these things by working out the ratio of the angel gold to the silver as it was being proclaimed in the details that we saw. Now, the angel gold was almost pure. In other words, stated to be anyway, 191 parts gold in 192. As opposed to the new gold coins, which were going to be 22 carat gold, that is 22 in 11 parts in 12. Here is Harriot's calculation. On the right-hand top, you can see the ratio of gold to silver. Now, that's about the only explanation there is. He never wrote much explanation of what he was doing, but by looking carefully at the calculations and the signs and the numbers, we can work out that he is in fact working out the ratio as it applied to angel gold and sterling silver, but in 3 different ways. So he first of all worked out the ratio in the way analogous to the way it was given to in the proclamation. In other words, the ratio in terms of the coined metals, the angel gold and the sterling silver. That came out to be 11.6129. He then went on to a fact that was more pertinent to the international markets, and that was not the alloyed metals as they appeared in the coins, but the pure gold and the pure silver. So if the alloys were to be reckoned as of no value, that is, if the additional metals in the coins were to be disregarded, and we just worked with the ratio of a pure gold to pure silver, we actually get a ratio of 10.7981. And even more tricky, he also did the calculation saying, well, that's all very well, but actually the silver, the gold coins, the alloy is actually silver in those. If we are regarding silver as a metal of value, we ought to reckon for that the silver in the gold as well. In fact, it makes very little difference, as you can see, and that, of course, because the angel gold was, in fact, almost pure gold. So why would Harriot have done these calculations? Almost certainly, he was asked to do so by Henry Percy for two possible reasons. One would be that Percy was a wealthy landowner and would have had a number of gold coins in his treasury, many of them the old angels which had been coined in the time of Elizabeth. Another more general interest would have been that as a member of the Privy Council, Percy would have been keen to know what should be proclaimed as the value of angel gold when and if any more angels were to be produced. In fact, it took quite a long time before such a proclamation was actually made. And the new angels, when they did appear, though there were relatively few of them, they were actually coined at a different value to the earlier ones. All these calculations were based on official data about the fineness of the coins. But Harriot also had reasons for looking at the facts more carefully, and he began to conduct his own experiments. And here we have an innovation in that he used the hydrostatic method. The hydrostatic idea, of course, goes back to Archimedes, but in fact the use of the principle for the numerical evaluation of the density of substances was relatively recent. And Harriot's papers contain a large number of notes of various publications from the last part of the 16th century, where scholars around the world had been starting to do estimations of specific gravity, as we should call it, using the hydrostatic method. Also, there is this little picture of a balance, which is intended to show a mechanism for weighing objects, not just coins, of course, any objects, both in air and then in water. So the details are best explained by looking at one of Harriot's experiments. He did a very large number of experiments of this kind. They're all a terrible mess and a scrawl, so I made a transcript of this one. In the top line, you will see in air, and then a symbol which is the symbol for gold. So, in fact, we can deduce from other scrawl that he was weighing 18 angels in air. Alongside that, there is a list of weights which he's used to balance those. And reducing the answer to grains, the total comes out to be 1408.5 grains. He then repeated the experiment, weighing the same parcel of gold in water, and gets a lesser value, 1329.5. So the difference is 79. And the numerical form of Archimedes' principle tells us that this is, in fact, the weight of the water that has been displaced by the gold. So from that, we can deduce, Harriot did deduce, the specific gravity, as we should call it, the relative density of gold in terms of that of water. So the ratio in that column at the bottom there, 79 grains of water occupy the same volume as 1408.5 grains of gold. And he then transforms that into taking the base as 1000 for water. Harriot did many experiments of this kind, and he also did some more tricky experiments. Here is the transcript of one of them. This is actually about trying to determine the specific gravity of the alloy in the coins, and the details are quite tricky, and I'm going to leave that there and refer you to the transcript of the talk. So we can now move on to the aftermath of this work and how it affected the fate of Harriot's unpublished papers and his reputation in the years to come. Harriot's situation, supported by his patrons, was in many ways ideal, but it did have its drawbacks. Walter Raleigh had always had a difficult relationship with Queen Elizabeth, and when King James came to the throne in 1603, he lost little time in having Raleigh arrested, put on trial, and condemned to death. King James magnanimously suspended the sentence, but nevertheless Raleigh was confined in the Tower for many years. This affair had a serious effect on Harriot because at the trial he was blamed for being a malign influence on Raleigh. But worse was to come, because towards the end of 1605, Guy Fawkes conceived the idea that it would be a good idea to blow up Parliament and the King and all the members of Parliament in it. The plot failed at the last moment, but it turned out that one of Guy Fawkes' fellow conspirators was Thomas Percy. This Thomas Percy was a relation of Henry Percy, Harriot's patron, and worse still, he had visited Henry Percy at Sion House on the day before the November plot. So Henry Percy and Harriot were taken off to the Tower, and Percy was interrogated at great length. No serious evidence against him was ever found, but nevertheless he too was confined in the Tower for about 15 years. Harriot was fortunate enough to be released, and eventually he was able to return to his scientific work. For example, he did a lot of experimental work on optics, the laws of refraction, and this led to his ability to view the moon's surface with a telescope in 1609. In 1611, his expertise in optics was put to a more mundane use when he was asked to make spectacles for the Lord High Admiral. The man responsible for this was the Admiral's secretary at the time, Thomas Aylesbury, and he will play a large part in the ensuing story. So, Harriot and Aylesbury remained on good terms after the affair of 1611 with the spectacles, and eventually Aylesbury was appointed as an executor of Harriot's will, with specific responsibility for his papers and hopefully their eventual publication. Aylesbury continued to rise in the civil service, and in 1627, that would be under Charles I, he became a master of requests and a baronet. Strangely, in 1632, he was appointed sole maker of balances and weights for the king's money. This appointment must surely have had something to do with his knowledge of Harriot's work and his papers, which contained, as we have seen, work on coinage. And indeed, Aylesbury rose yet further, because in 1635 he became the master of the mint. So regarding the papers, according to Harriot's will, the papers should be put in a convenient trunk with a lock and a key and placed in my Lord of Northumberland's library. There are also instructions about publication, and as we said, Aylesbury had to take charge of that. Matters went rather slowly, but after 10 years, Aylesbury, with the help of Walter Warner, another of Northumberland's associates, they produced a small sample of Harriot's work, which was published. It's a rather poor attempt to display what Harriot had achieved in algebra, and it contained nothing at all about the scientific work or the work on coinage. However, in 1634 and 35, we know that Warner wrote tracts on the commixture of metals for the mint. In other words, the matters about which we have been talking in the rest of this talk. Almost certainly, Warner did this at Aylesbury's request. But the power of the Aylesbury was relatively short-lived, because in 1642 the Civil War broke out. Aylesbury was, of course, a strong royalist. Warner himself died in 1643, and Aylesbury first of all went with the king to Oxford, which was the royalist headquarters, and when Charles was eventually executed in 1649, Aylesbury decided it was time to go abroad. As far as the work on coinage is concerned, it seems that it remained of interest to the powers that be, because here we have this note in 1650, the Commonwealth time, which says that Mr. Ward, the professor of mathematics, the professor of astronomy at Oxford, is to set out the mathematical and other works of Warner on coins. This comes from Hartlib's Ephemerides, a book of gossip which has an amazing number of useful insights into what was going on at the top of the tree in the land at this time. However, nothing apparently came of that, and all we know is that Aylesbury died in exile in 1657. The story of Harriot's papers after that is a sad tale indeed. It was not until 1784 that a large collection of Harriot's papers was in fact found at Petworth, which is one of the Northumberland residences, not the one in London. This was his country residence. And although the discovery was a great event, the subsequent events were by no means so good. The discoverer of the papers seems to have set about distributing and disordering them in a rather random way, and in 1811 some of them finished up at the British Museum. The British Museum bound papers as they were presented to them, which was in a totally disordered state. And in fact, it was not until 200 years later, 2011, that it was possible to examine these volumes seriously, because in that year, 2011, Harriot's papers, the surviving ones, were published online, partly as a result of the work of the late Jacqueline Steddle. The publication included the British Museum volumes and the papers that had been left at Petworth after their removal. So, what conclusions can we draw from this story? Well, we can be sure that Harriot's papers did contain material on coinage because we have seen it. We know that some of this material survived, and it seems likely that there may have been more papers that were used by Warner, perhaps taken by Aylesbury when he went abroad, and have totally vanished. Aylesbury certainly had access to and was in fact in charge of all Harriot's papers as a result of the wishes expressed in Harriot's will. We also know that the papers were regarded as important for the work on coinage, as well as the mathematical and scientific work contained in them. The Royal Society had tried hard in the 1670s to locate the papers, but they were totally unsuccessful at that time. And as I said, it was over 100 years later before the box of papers was actually discovered at Petworth. So I'm happy to answer any questions. There is, I think, going to be a question session, and you have the transcript, which is provided by Gresham College. For those who want to read more detail, the talk is based on my paper with the same title, which appeared in the Archive for the History of Exact Sciences. And there are a couple of other publications of mine which contain relevant material, specifically enlarging upon the numismatic side of the work that Harriot had done. So, thank you for listening.